Everyone, welcome. Hopefully you can hear me. Feel free to say hi in the chat. I'm just having a little look at the chat and can hopefully see any comments, questions, and answers as we go through it today. I hope everyone's well. Please do feel free to say hi in the chat so I know that you've joined us and that we've got people here live. I'll be starting sort of shortly anyway. We're going to look at differentiation from first principles today, which is a brilliant A-level pure topic that didn't used to be on the A-level single maths course. I didn't see it until I was at university, but it's a brilliant topic to be looking at. But welcome. I hope you're all doing well. Everyone's having a good week. Everyone's keeping well. And thank you for joining us, those that are here. Feel free to say hello. As I said, if you've got any questions, any comments, as we go through the topics today, please do share those in the chat and hopefully I'll be able to see those as we go. But as I said, welcome to everyone and thank you for joining us. I'm about to share the slides and we'll get started shortly. But yeah, welcome to everyone. We're looking at differentiation from first principles. If you could let me know as well if this is a topic you've covered before, if it's something you've seen. I know for a lot of students, it's very new at A-level. So that's what we'll be doing. We'll be looking at differentiation from first principles. And as I said, please do feel free to say hello in the chat today now and answer any questions as I share them. So let me just share this and hopefully you guys can see my screen. And we'll get started shortly. But thank you for joining so promptly as well. And yeah, welcome. I hope everyone's having a good weekend. As I said, we're looking at differentiation from first principles. And we'll be going through, I'll try and answer questions as they come in, but also talk you through the topic and then hopefully build up to some exam practice as well. Great, but as I said, do feel free to say hi. Thank you all for joining. We're going to get started now. I'm ready to go. Great topic. And yeah, let's make a start. So differentiation from first principles. I'm Max. I'm kind of the lead maths teacher at Snap Revise. And I did a maths degree a few years ago and then have been teaching A-level maths and GCSE maths pretty much ever since. And what we're going to do today is I'm going to look at the topic of differentiation from first principles. Welcome to everyone joining. Please do feel free to say hi, ask any questions throughout, and also share any answers if you're kind of ahead of us and know what's kind of coming up. I'm also going to quickly mention that we have the A-level exam crash courses coming up soon. So as I'm sure you're all aware, we're kind of almost at exam season now. These are brilliant live sessions for biology, chemistry, physics, and maths, where we really go through the content of the courses really carefully and make you kind of exam ready. So it's a kind of crash course that's run at Regent's University, and it can be accessed by live stream. So this is coming up very soon. Hi, welcome. I can see some comments coming through. I'm just going to spend a minute or two just showing you guys this because I think this is a really good opportunity for those approaching exam season if this is a big year for you guys. And then, as I said, we'll be looking at the topic of differentiation from first principles today. Hi, welcome. Thanks for saying hi in the chat. And hopefully everyone else can hear and stuff as well. But yeah, these sessions look at exam technique. We go through the questions step by step and basically kind of work through all of the content on the pure and applied sides of the course. And show you kind of how to model answer the stuff and get really prepared for the exams coming up in May and June. So that's taking place over Easter. And it's kind of a really good tailored revision course that really finally goes through every part of the course from the sides of pure to stats and mechanics and teases out the ideas for exam questions. So that's worth checking out. There's really lovely seminar booklets that are kind of crash course material that's, I think, brilliant for the exam because it kind of is something to take away and reflect on. And you can really tease out the ideas in light of exam questions, just like we do with the web classes, but in a much kind of fuller scale. There's also a tutor messenger, so you get like live support on the day, and we can kind of discuss it with everyone if you want to send your questions in, but you'll get instant feedback. So it's a really, really good kind of event to be part of in preparation for your exams. And these are the dates. So they're coming up very soon, and that's why we're kind of mentioning them at the start. You can take part live in person at Regent's University, which is a lovely venue, and live stream via Zoom as well. So there's tickets for both available through Snap Revise. So please do have a little look at that. And so I wanted to mention that as it's pressing, coming up soon, and while we're all here. But I think we're going to get started now. If you're interested in that, please do check it out. It'd be lovely to see you guys at the crash courses coming up soon in the Easter holidays. So what we're going to look at is we are going to do differentiation from first principles today. Please let me know in the chat if you've done this before, if this is revision or if this is brand new. So we're going to revise what the idea of a limit is, look at binomial expansions, and then also look at what first principles is as a process. Lovely. So for some people, you've seen this before, but we're going back over it. Excellent. This was very new to me when I first saw it. Like, I don't even think I saw it at A-level, as I said. It was at university. And even the ideas of limits from A-level maths was very abstract. So for some people, this is revision, and that's fantastic to hear, because this is something that, as a new thing on the A-level course, is quite likely to be examined, I feel. So I think this is good to go through. Just in terms of prerequisite stuff we should already know. This is going to be sort of from the year 12 perspective, but we're also going to go into a bit of the background that would spill into the year 13 first principles as well. So just very much from scratch, yes, so we're going to start with the binomial ones, which is like the year 12 kind of style stuff. But in terms of the context of it and how it works, obviously we should hopefully know that gradients refer to steepness of graphs, and that is actually the point of differentiation. And a lot of the calculus we do in both year 13 and year 12 is that we know from GCSE a straight line has a constant gradient in the form y equals mx plus c, and it's effectively just the change of y over the change of x. However, when we're dealing with curves and more complicated graphs and functions in the kind of calculus topic, we have to look at rates of change from the point of view of differentiation, because we know that the actual gradients are changing. And this filters into mechanics as well. We see it a bit in that part of the course. So just very much a quick recap of differentiation. Hopefully we're aware there's different notation we can use, dy dx, f dash of x, but it's basically finding out the gradient. No worries, thank you for the check-in as well, guys. So I'm glad we're all really very much in tune with the fact this could come up both years. Gradient of the tangent. And the notation is important because we want to be consistent with the question. If they use f of x, use f dash of x. If they use y, use dy dx. And the actual way to differentiate a function that's a polynomial, the sort of most basic scenario that we see sort of in year 12, is to basically times by the power and then drop the power by 1. And then we should also be familiar with binomial expansion. Again, this is very new to a lot of people at the start of year 12. So this ends up being a kind of formulaic approach where we times by the combination kind of aspect to work out how many ways there are of achieving it. A to the n minus r, b to the r, and so on. And n choose r is given by this formula. Does everyone recognize binomial expansion? I know, again, this is quite a new topic for a lot of people. So that in itself is a scenario. So you can imagine this is quite a big question if this comes up, because it kind of hits quite a few topics at once. It tests, do you understand differentiation and what we're doing? Do you understand binomial expansion? So it's a really good topic from an examiner's point of view. Excellent. Right, let's keep going because I'm keen to get on to limits and first principles. So this is something that's now part of all of the specifications since the A-levels were changed in 2017, and limits and differentiation from first principles are really crucial. So we're going to start with limits and the idea of a limit. And this is kind of the background of what we're going to use in first principles. So in terms of what a limit actually is, a limit here, we're going to just define the limit of a function f of x as x tends to a is basically the value, and do feel free to have a think ahead at these questions here for this function you can see the graph of, because it's a little bit weird. Limits might be a very new idea to you guys. So have a little think about if you could answer these questions. I'm just going to define and remind you what a limit is. So the limit of the function f of x as x tends to a is the value that the function f of x gets closer and closer to. We might recognize it as a sort of asymptote, and closer to. Brilliant. I can see some answers coming in, so I'm going to try and catch up with you guys. Well done. As x gets closer and closer to a, where a is a number. Right, let's make sense of that now. Very good. So some people have shared an answer already, and I think that answer looks brilliant. So if I just draw in at this value here, when x is 2, this is when x is 2, we can actually see that that's an asymptote. Is everyone familiar with an asymptote? So something that is infinitely approaching, but sort of magically never quite touches. It never reaches, but is always on the kind of ascent or approach towards it. So absolutely right. Thanks very much for the suggestion in the chat. As x tends towards 2 and gets closer and closer to 2, the function is actually approaching infinity. It's just growing massively and getting closer and closer. The nearer you get to 2, the bigger the output. And the more you zoom in, the more that scenario takes place. Does that make sense to everyone? So this is a little bit of a sidestep from first principles to start with. It's the idea of a limit. It's the idea of taking something to the extreme. If you zoomed in extremely or you carried on extremely, what's going on basically overall? Can everyone see that as we get closer and closer to x being equal to 2, the output zooms off massively, basically to infinity? Does that make sense? And then this one is quite a different question, because this is saying as x goes to infinity, as x gets bigger and bigger, what's the limit of the actual function itself? What's the limit of the actual output? Does anyone have any ideas for this? So this is effectively saying, like, what's the limit of the y values? Where as x goes on forever and ever, is there an asymptote, a horizontal asymptote that it will never cross or never reach? Excellent, really good. And thank you for sharing answers, guys. This is really good. So good idea. It looks like it would be, actually, I think the asymptote is going to be, drawn that in terribly, sorry. The asymptote is actually going to be at 1. So it looks like it's a bit higher than the axes, but as x approaches infinity, it looks like it's infinitely approaching that line 1. Does that make, yeah, excellent. But worth clarifying, because often the axis is an asymptote for certain graphs. So that's like a sort of definition of a limit, and it really ties in with this idea of asymptotes. So we're going to do a little bit more breaking down the idea of limits before we really hit first principle differentiation. And as I said, this is a massive kind of quite abstract topic when you first do it, but really worth going through. So let's move on, but thank you for the questions and answers there. That was really, really good to check. Here we go. So I'm going to just carry on with a few more notes. Feel free to screenshot, ask me to go back or anything if you want to check it. What we're going to look at here is we're going to look at the fact that if we have a limit of 2 functions added together, we can actually break that down as 2 separate limits. So this might, for some people, seem obvious, and for others it might be worth us taking the time and going through. But does it make sense that the limit of 2 different functions added up is just the limit of each one added up? So you can do them separately. And that's kind of where there are limits as it tends to a, as long as you're tending towards the same value. Okay. So yeah, excellent. And then this thing is just a point on notation. I don't want this to confuse you. This is largely the sort of start of first principles, which we do in year 12, but we're kind of talking around it a bit more broadly as it does come up for calculus of trig functions in year 13 as well. But we're going to start with the binomial expansion aspect of it. Right, so the other thing I wanted to say is if we have x to the power of n, and x is getting closer and closer to 0 to the, so this one, what we're going to have, when n is greater than 0, so for example, a positive power, and this is a really tiny number, close to 0 is what we're saying, the limit will be approaching 0. When n is 0, anything to the power of 0 is 1. And when n is less than 0, this is actually going to approach infinity. So this is just sort of a weird separate idea to think about, is that for numbers close to 0, think about what their powers are doing. 0 to a massive power is actually getting smaller and smaller, or as in a number very close to 0, like 0.0000 something. As we increase the powers of that, it's just getting smaller and smaller. So the limit is actually approaching 0. Then when n equals 0, anything to the 0 is 1. And then if n is a negative number, a negative power, 1 over a tiny number is a really massive number. Yes, exactly. It's a really, really good question. And I think this abstract concept of a limit is really strange because it sort of feels like, is it an okay answer? Is it bang on? Is it exact? And it is more of a sort of conceptual thing. So it's a really lovely question that as it approaches the value, it doesn't actually reach it. So you're looking at it kind of zoomed out, big picture. What is the overall effect if you took this to the extreme? So whilst it's never actually maybe approaching it, there is a finite value that's a limit, effectively. It's not going to cross. So that was a really lovely question. And it is that sort of teasing out I want to do because we don't meet this at all before A-level. Now, here's a really good question to go through because this will directly tie in with first principles in a minute. Now, this one says the limit as x gets tinier and tinier and closer to 0. What does this whole thing tend towards? What does this function become? So if you're ahead of me, please feel free to share answers, but I want to show you kind of from an exam point of view how we would answer this. So this is very like what we're going to see in a second with differentiation. So as 3x plus 2 to the 4, that is a binomial expansion, and it is a little bit tedious, so I'm going to kind of help you guys out with this, but it's kind of good revision as well. So if we expanded that kind of binomially, we're going to get the following, and just check you agree or you think, yep, I could have got there myself. So the binomial expansion is a key topic that really comes before this because it's crucial in what we're doing. And hopefully you will recognize that. So that's kind of the first quadruple bracket expanded. And then what we do is we've got this minus 16 on the outside as well. And then that's all divided by x. So for those of you that have done some first principles, you'll think this sort of kind of smells a little bit like it. You're right, it is very like it. We use h and we do some other stuff, but this is what we've got. Let me just have a little read. Yes, okay, good. So we've got to kind of tidy this up now. So brilliant suggestion in there. If we start dividing, so that 16 will be cancelled by the minus 16. And x will cancel a lot of aspects of the numerator. So we can certainly tidy this fraction up a little bit. And then I think that question was brilliant. I just need to reread that again. But yes, it's this will become 81x cubed plus 216x squared plus 216x plus 96. So for those that wanted to clarify that, x cancels with each power in here, and we end up with the following. So we're looking at the limit of 81x cubed plus 216x squared plus 216x plus 96. Now, as x approaches 0, I think this is exactly the question we were asking. What's the net effect? Exactly, it would tend to 96, because what we're saying is x is getting closer and closer to 0. What does that really mean when I've got 81x cubed and something x, 216x? Everywhere it's being multiplied by x is dwindling away to nothing. Effectively, x is becoming more and more negligible. So anything with an x attached to it is turning into something that has barely any effect. It's dwindling away. It's becoming effectively pointless, useless. It's gone. It's disappearing. So this will disappear. This will start to disappear. This will start to disappear. And the only thing that will be left is this constant value of 96, because that's not going to cancel out. That's independent of x. Whatever x is doing, x is shrinking, we're going to be left with 96. So the limit of this function is actually 96. And so it's like, felt like a lot of heavy algebra, but actually what it gets you is the net effect of all this stuff as x is close to 0. Basically, this is getting closer and closer to a true value of 96. Okay, so that was excellent. Hopefully the binomial expansion is clear. I'm happy to go through it if not. But basically, this was the binomial expansion of 3x plus 2 to the 4, whereby you would do 4 choose 0, and then times 3x to the 4, and then that would be times by 2 to the 0, and so on. And hopefully you know the binomial expansion stuff. But what I wanted to do, because I think there were superb questions and answers there, we're going to get onto the actual differentiation now using this skill. Could I just do a little checkpoint to get a sense of how we feel? It looks like a lot of you are quite confident with this already in terms of the idea of a limit and how we're going to use that within differentiation. But if you could just give me a 1, 2, or a 3 as a just kind of honest reflection on how you feel with limits so far up to this point, the bit we've covered. And I know from the chat that some of you are already asking, is this year 13, is this year 12? Because you know that this topic grows. But just to give me a sense of, yep, I'm confident with this so far, that would be fine. For some people, this is very new. So if this is quite confusing, it might be something you need to spend a bit more time reading over, but then practicing examples, much like the one we've got, because it is in all the textbooks and it is in all the courses. So we'll go through a couple of quick exam questions now to reinforce that. And then we'll start first principle differentiation properly. No worries. Thank you for kind of the honest reflections on that, because it is, I found immediately a difficult topic when I first met it. Hi, welcome if you're just joining. What we're going to do, we'll follow up those examples with some exam questions now. And I think these are actually really good ones because they're a little bit different. And then we'll get into the differentiation, and hopefully it'll be a bit nicer going through the practice of differentiation. So evaluate the following limits for when x approaches 0. So what we're thinking about is if x gets smaller and smaller as a tinier and tinier decimal, what does this thing do? And there's no problem with actually in your head or in the calculator subbing some values in and thinking basically what's happening. So the limit as x gets smaller and smaller and closer towards 0, like 0.1, 0.01, 0.001. Right, now, if it was just x, it's decreasing. What's weird about this is that when it's 1 over x, when it's sort of a reciprocal scenario, or 1 over x squared, if the denominator is getting smaller and smaller, does anyone know what that actually does? It does increase massively, because I'm dividing by a really tiny number. So if you do like 1 divided by 0.2, 1 divided by a fifth, you'll see the answer is 5, because you're basically saying how many times does this tiny number go into 1? And as that number gets tinier and tinier, it will go in more and more times. So it become massive. So actually, the limit of this is actually positive infinity. As you get smaller and smaller and you divide by a smaller and smaller number, the answer is actually bigger. And this is something that throws a lot of people off. So 1 divided by a tiny number is actually a massive number. Has everyone seen that before? Because it's maybe an idea we often forget, or we don't go over. But the limit of 1 over x squared as x is getting smaller and smaller is actually, it starts zooming off to infinity. It increases massively, exactly as we said. So very well done if you spotted that. Does that make sense? Is that okay? We're going to try the others as well, because I am keen to get on to actual first principles use of this. Well done, brilliant. Now, please do feel free to ask any questions or challenge any of this, because I do want it to make sense. This second one is actually, I think, relatively challenging. So I'm going to put a bit of space for it over here. What we've got is again, the limit as x approaches 0 of x squared times by 2x squared minus 2x to the minus 2. Now, remember we mentioned earlier that you can split the limits up. So I would personally expand this bracket. I think this is maybe an easier way of doing it. And we get 2x to the 4 minus, and then when you times, you add the powers, don't you? So x to the 2 times x to the minus 2 is x to the 0. So that would just become minus 2. And they would effectively cancel each other when you expand. And now we're doing the limit of this. Very good. I've got some brilliant answers and questions coming into the chat, like consistently being sent through. So thank you for that. We did mention earlier that you can split this up, which is great. You don't actually have to split this one, but you can. But basically, as x approaches 0, that whole bit there is going to go. And the limit as x approaches 0, 2 is still 2. So the answer is actually minus 2. This thing will approach minus 2. Very well done if you've spotted that. We'll approach the constant term. As we said, lovely, well done. Very well done if you've got that. So that was, again, it might not have been the style of question we've seen before, because you've seen limits in the context of first principles, but this idea is really worth going through. Lovely. Thank you so much for suggesting, and don't worry if you're wrong. I think the questions and answers that have been sent in have been brilliant, so really, really good. Let's just do this last one, and I think that will tie us nicely into really introducing the idea of first principles. So let's give it a go. The third question here. So we want to do the limit, and this is again another interesting one because we've got different letters going on, of x plus 2y cubed minus 8y cubed over x. Okay, so I'm going to do the binomial expansion of that bracket first of all, and it would give us x cubed plus 3x squared, and we'd have to times that by 2y plus 3x times 2y all squared plus 2y cubed all cubed. So I'm going to run out of space here. Let me just create a bit more space, hopefully, for myself there. So this will become x cubed plus 6x squared y plus, well done if you're ahead of me. Brilliant. And please, if others can check they agree, you guys might beat me to it with this one. But very good. So, blimey, I'm running out of space. Is it okay, guys, if I clear this? The answer to this one was -2. The answer to this one was plus infinity. What I think I'm going to do is make sure I have a bit more space here. So that answer was -2. So what we've actually got is we're going to have that the limit as x approaches 0 of this thing expands to x cubed plus 6x squared y plus 12xy squared plus 8y cubed. And remember, in the actual question, we were minusing 8y cubed off all over x. And I think that's fantastic. Some of us have got there already. We cancel that down. Then what we're going to end up with, been writing a bit too big today. Here we go. This will come out as the limit of x approaching 0 of x squared plus 6xy. And basically, as some of you have noticed, well done, guys, anything with an x in it disappears at this point. And so the limit is 12y squared. That is absolutely fantastic. And you don't need to say or do any more than that. That is the limit. So that's fantastic. And great to see some of you answering that in the chat. Well done. So let's keep going. We're doing really, really well here. We are going to really hit differentiation from first principles now, which uses that skill. I do want to talk about the context of what we're actually doing with this. So, right, in the method that we're going to see, you do need to be clear with the notation, and it's actually the letter H we're going to use. We're going to look at what's going on with first principles. So finding the gradient of a tangent graphically is basically like if you were to go to each point, work out change of y over change of x, and you use loads of little straight lines to do that. The smaller and smaller you close the gap, the more the limit is going to reflect the true gradient at that point. So what we've got is the gradient of a tangent to a point of a curve is equal to the limit of the gradients of the chord from that point of the curve. And what I'll do is I'll put this in a context in a second where we'll see it with an actual curve that we're going to use. From that point of the curve to points closer and closer Okay, so what we're basically saying is, as we take the limits and we close the gap, it effectively ends up telling us the true gradient. Okay, yeah, so we'll look at some examples and then I'll double check your question again. Is it possible for this to be? Right, so normally things cancel out, but we'll go through like what's actually happening as well to kind of see, but it's a really good point. And we'll see that there's sort of a familiar style of questions. So it normally does tidy up nicely if it, the question is designed well. So just to check, who has seen this first principles formula before, whereby we say, and I think for some examples, they actually give it to you in the formula book, but it's given as f of x plus h minus f of x all over h. And I actually want to just explain what this is, but please let me know if you're familiar with this. Because what this basically is like saying is like if you've got, say, for example, a curve and you have an input of x, and then you have another point and you have an input of x plus h, the output of this is like the y value is like f of x, it's like x subbed into that function. And the output of this is f of x plus h. So had it been a straight line, the way you'd find the gradient is the change of y over the change of x. So the change of y is like f of x plus h, that output, minus f of x, that output, divided by the change of x, which is this small distance h. Now, if we're making h smaller and smaller and smaller, what we're effectively doing is closing the gap and then looking at the net effect of the gradient at a single point. That is what first principles is. So it's still doing differentiation, it's still doing gradients from the point of view of change of y over change of x, but we're now thinking of it much more holistically and kind of abstract maths way of looking at it, that it's the net effect of the change of outputs over the change of inputs as we close the gap into a single point. So it's a really kind of deep way of thinking about this. But we're going to go through and look at this example here. And I know for some of you, you have seen this before. Right, let's have a little look. So for x cubed, if I was going to apply this formula here, this kind of first principles limit formula, we're basically saying what is the limit of, as h approaches 0, of x plus h cubed minus x cubed. Right, brilliant question. I'm just going to clarify that. So before I do this, can anyone just differentiate x cubed for me the easy way without first principles, like instantly using the little rule we learn in year 12? What is the derivative of x cubed? Anyone know what x cubed should? Yeah, exactly. 3x squared. So in answer to the question, if they just say differentiate, like if we just need to differentiate x cubed, you can just say 3x squared. You don't need to use first principles. If they specifically ask you to differentiate by first principles, then you have to use this method. And it is a little bit more involved. It's a bit more long-winded. But in general, you wouldn't do first principles unless you were told to do first principles. So normal differentiation is much quicker using the kind of rules we've learned. Does that make sense to everyone? So you don't use first principles all the time. It's only if it comes up as a style of question. And if that's the case, it's probably because they're actually testing that you understand binomial expansion and other stuff as well. So what we're basically doing here is, for the first principles of x cubed, we're looking at what's the output of x plus a small gap cubed minus x cubed itself divided by the small gap h. So it's like the change of y values over the change of x values, which is tiny, and we're closing the gap. So we're honing in on a single point and looking at the net effect of the change of y over the change of x. And so what we have here is, if we do the binomial expansion, which, as you can see, that's more of what this is a test of. Can you actually expand a triple bracket and tidy it up? So x cubed plus 3x squared h plus 3. And thank you again, guys, for the questions. They're spot on and really worth teasing this stuff out. Please do ask me to clarify if anything is still not clear. Up to here, are we good? Does this make sense? Or are we following this method for this particular example? So that triple bracket expansion, which I've done. Yeah, excellent. Okay. So this does tidy up. Lovely. Brilliant. Yes, good question. That sort of thing is more likely in year 13, I think. Algebraic fractions, there's an element of it in year 12. You do in year 13, and what you can do is you can use polynomial division. Or there are other techniques in year 13 as well. In year 12, you shouldn't need to do anything particularly difficult with differentiation with algebraic fractions like that. I would be careful using resources online. Like, I know a lot of the websites with resources are brilliant and they have solutions and stuff, but do bear in mind that the A-level really did change a lot in 2017 and got repackaged. So some of the stuff on many of the websites are like for old courses and stuff. So they're still excellent revision tools, but they might not be quite in line with how the course has been packaged together at the moment. So just kind of bear that in mind. So what you could do is, if you're looking through answers of questions like that, do look out for where it was from and the date of it. And if it was sort of pre-2017, it might not be in line with what you need to know at this point, if that helps. That's a really good point, and being careful with the resources is really important. Yes, brilliant thing you've spotted there. That will generally happen, which will bring it down, which is like why when you differentiate, the sort of powers come down and it becomes like a lower level polynomial. Really good, really well spotted. So well done. And thank you so much for the questions and the points we're making here. It's worth teasing this stuff out. But yeah, I would suggest be a little bit careful with the resources in terms of if they're a little bit older, because they're still probably brilliant overall, but they might not be packaged completely right for what you're doing. So this is what this will boil down to when you cancel your H's out. And then everything with a h in it is going to tend to 0. And look what we're left with. Ta-da! Got there eventually, 3x squared, which is what we want. Yes, exactly. So the question was, for the power, do we just put x plus h to the power? Yes, what you do is you just put x plus h into whatever the function was. And this function was something cubed. If it had been 5x cubed, then you would do 5 brackets x plus h cubed. So you stick x plus h as the input into whatever the function was. Really good question. And please do keep those questions coming along in the chat, because that is great. And we're going to see that now. So give me another little update and be honest, if you're at 1, 2, or a 3 with how we're feeling with this, because what we're going to do now is look at a couple of really nice exam questions. And I think actually this topic feels worse than it is when you first meet it. And then when you see it in exam questions, you're like, okay, there's a very set kind of way it will come up. No, so you do need to, I would say you do need to denote limit as h approaches 0 in your working, so that they know you know that's the limit. But I wouldn't say you need to write any words or statements or sentences. You set it out like this, and we're going to model this now. That's good enough. Okay, so I'm going to do this next question as very much an exam style model. But yeah, please let me know 1, 2, or 3 how you're feeling with this content. Cool, and thank you to those that have. Right, so let's have a little look. No worries, here we go. Here's an exam question for us to look at. And this is exactly how I would lay it out. So I'd say the derivative of x, we know, let's look at the first principles formula. It's as h approaches 0, the output of the function plus h minus the output when we didn't plus h, all over the small change in x that we are calling h. So in this context, we're subbing x plus h into a function that raises it to the power of 4, and we're minusing off x to the power of 4 without a small change subbed into the input, all divided by this small change h. Okay, so we are going to do the limit of this thing now as h approaches 0. I'm going to open up those quadruple brackets, and on the top I'm going to have x to the 4 plus 4x cubed, and hopefully you can see how important the binomial expansion really is for this topic. If anything, it's the main thing being tested. Can you expand these brackets? Which is why as well, I don't think they're going to give you massive powers, like they won't have a 10-term expansion. It will be maybe 3, 4, or 5, but it should be a relatively straightforward one, hopefully, because it's already quite time consuming and feels a bit tedious. Now, again, we can cancel the h's down. So let's do that. Okay, and what do we get? Well, we get from this stage, oh, sorry, and that cancelled that, didn't it? Brilliant. 6x squared h plus 4, I got a bit confused there myself. Plus h cubed, and can anyone tell me what's going to happen here? Hopefully we're seeing a bit of a, sorry, that x to the 4 is gone. This is what we've got the limit of. As h approaches 0, as we close that gap, and h is becoming redundant, it's becoming more and more negligible, all the bits with a h in it are getting closer and closer to 0, so effectively diminishing away to nothing. We are left with that the limit is equal to 4x cubed. So that is the gradient function, that is the derivative of x to the 4. That describes what the steepness is doing at a single point. That's the net effect of the gradient. Okay, so hopefully that's good, but we'll do another exam question now. And this next one is really good. for being careful about what we sub in. I think this next one is brilliant. Am I okay to move on? Is that okay? Yes, you cancel the h's with the denominator to sort of tidy up that fraction and see the overall effect. Yeah, good. So here we go. I think this is a really, really important one to do, because this actually shows if we understand how to sub x plus h in. This is a much more involved looking function. So I'm going to go through this carefully and let's see how we go. So what we're doing, we're going to do dy dx. This time we've used that notation. This is, as I said, I think a brilliant one to look at, because what we're doing is, remember, instead of x, we're putting x plus h, but we're putting x plus h wherever there was an x originally, wherever there was an x. So what we've actually got is 7x plus h squared that's like your f of x plus h. And then your f of x is like this bit. And I think if we can follow this, we've got it. So let me just check we're okay up to there. Let's have a little look. So what we've done is wherever there was in that quadratic thing, wherever there was an x, we've replaced it with x plus h. And then where there is, and then we're also taking away x subbed in. Okay. So now it is a little bit of work with the algebra, but it should still tidy up. So I think this is a really good one to go through. So please do ask if you're a little bit unsure with any of that. But we've got to try and make the link with this one because it's a really good exam question to look at. So let's start tidying it up. So that will become that's that first bit. Yes, they should be. Yes, you can go over because I do appreciate this is quite a lot to take in. Some of these questions are quite full on and heavy content, but really good ones to do, hopefully. Right, let's keep going. Check we agree. Check we're sort of keeping up with that. Okay, so from here, what we're going to do is carry on cancelling this down. And what we'll hopefully see is that there's multiple things that are going to cancel out now. The 7x squared will cancel with the minus 7x squared. Also, this is minus minus, so the minus 6x, let me actually open this bracket up, be minus, the minus 6x minus minus 6x, that will cancel, and the minus 3 minus minus 3, that will cancel. So what we're going to be left with of the following: 14xh that's what it will boil down to. Okay, now I can cancel the h's. Tell me if you've worked out what we've got. It should equal now if you differentiated this from scratch, well done. Do check it the easy way. 7x squared would become 14x and minus 6x would become minus 6. So it does work. So it should work in this and ultimately get you to the answer you should know. But it's a lot of minuses. We had to be careful cancelling there. But do you guys see that the good thing about differentiation from first principles is you do kind of know what the answer should be, because hopefully it's something you could easily differentiate the easy way, and you could kind of know what you're aiming for. That's the other thing that's really important, is that I should be able to differentiate that quadratic and know the answer is 14x minus 6. I just need to be able to get there using first principles, which we have. So the hardest thing was subbing the x plus h in everywhere, expanding it all, and then cancelling the minuses. Yes, exactly. I would do that. I would say, look, I know how to differentiate that easily, but differentiation from first principles is its own thing. It's quite involved. So I'll do it firstly in my head and know what I'm aiming for. And then I'm going to just carefully go through the method, because then you know you've got the answer right. If you get to what it should be, you can move on confidently. So absolutely do that as a guide. Let's do the next one. And I think this would be good. We're doing really well with this. So a couple more. Let's have a little look. So this one here, this is differentiating at a specific sort of point, and let's see what we get. So firstly, this is just part A, they've broken the question down. Find f of 3 plus h. So what this is like saying is putting in 3 plus h as if it's x in the original function. So that would be 3 plus h squared minus 4 lots of 3 plus h. So wherever you see an x, you replace it with 3 plus h plus 2. Let's tidy that up. And remember, that's a sneaky double bracket. So it's 3 plus h, 3 plus h. Do bear that in mind. And we've got to be careful with that. Minus, we tidy all of this up. Plus 2h, and 9 minus 12 plus 2, so 9 minus 10 minus 1. That's what that tidies up to. Okay, so we're going to use that in the next part of the question. Feel free to screenshot, feel free to ask any questions, but that's part A. So they're kind of guiding us in to first principles here. Now it says the curve with that equation passes through the point 3 minus 1, where the x coordinate, then we're going to pick another coordinate, 3 plus h, meaning a small distance away from where x was 3. Use first principles to show the gradient of the tangent at the point. So this one's a sort of number answer. So remember that we know that the gradient is the limit as we close the gap, as h gets closer to 0. And we can do f of 3 plus h minus f of 3 all over the small change h. So instead of just saying from a generic point x, it's now saying from a point where x is 3 and a small change from 3 of h. What's the actual gradient? Well, what's really cool is I've already done 3 plus h in the first part of the question, and it came out as h squared plus 2h minus 1. And I actually know that the output of f of 3 is minus 1. You could put 3 in as x and work it out. How did I know so quickly that the output, or the y value, I'm kind of giving it away, is minus 1? I know that if I put 3 into that function, it will come out as minus 1 because they gave me a coordinate that's on it. But I could just substitute 3 into the original thing and see what comes out as y, and it should come out as minus 1. And then that's all over h. And then if I tidy this up, so h squared plus 2h minus 1 minus minus 1, that becomes h squared plus 2h over h. Hopefully we've seen it. But what we've got is that the limit is 2. So the gradient at that specific point is 2. So of course, using differentiation, the old-fashioned, old-school way, you could go just differentiate it, sub in x is 3, and work out the gradient at the point when x is 3. has actually got a gradient of 2. But what we've done is we've used that in the first principles setup. Yes, good. And again, that's really good, brilliant mathematician way of doing it. Check it another easier way. Check it a different way. If you get the same answer, that's good verification that you know what you're doing and it's worked. Well done. So it works exactly the same as with x, as if x was a number. You've still got to do a small change h, but you're carrying that number through and all the negligible bits are still disappearing. And then you're just left with the numerical gradient value at that point. So it's a really good technique to practice. And actually, once you do a few more of these, it becomes very samey. And once you're at that point, you've learned it, you've done enough. So whilst when you first meet it, it's a little bit of a strange topic, don't forget, you can check it the easy way and know what you should be getting as your answer. So that does help. And also, once you want to practice this to the point it feels samey, even if you think I still don't quite get the kind of abstract goings on in the background, at this stage, it's a technique we can work through and practice. And effectively, it's a case of subbing in outputs of functions over inputs, cancelling it down. It's very heavily algebraic, but what that's representing is the net effect of a change of y over a change of x. And it sort of then basically is the design of the machine behind gradients, the function that creates a gradient stems from a kind of shrinking line representing the gradient at a fixed point, a tangent, as the gap gets narrowed down from outputs and inputs. So you're comparing 2 points, you're closing the gap, and the net effect of that describes the gradient function. So that was really, really good. Thank you so much for questions and answers throughout. We've hopefully understood what's meant by a limit, even though it is a bit of a strange concept. We've seen the importance of binomial expansions, and actually that largely first principle questions are testing binomial expansion as a skill. And we've understood hopefully graphically and algebraically what we're kind of doing in the background by first principles. But I think it was a brilliant suggestion that we actually use the easy style differentiation to kind of go through and check your answer so you know what you're aiming for. That was really, really good. Thank you for the questions throughout, though. If anyone has any quick questions, feel free to ask. Brilliant. That's really, really good and really excellent feedback and questions and answers throughout. And in answer to some of the earlier things about resources and practicing, welcome and thank you again for those taking part. Thank you for the questions. Hi, I can see some questions coming through. All I was going to say is just be very careful with mindful of the resources you use in case they are a little bit out of date. But this is absolutely a case of doing a bit of practice for. So do make sure you're doing that. That's great. No worries. So this session will be uploaded and you'll be able to watch back. So hopefully that's useful. I did mention at the start, there are upcoming crash course seminars at Regent's University. So if you're interested in that, they're, in my opinion, I think they work really, really well. They're fantastic seminars and they're a really good opportunity to tease out all aspects of the course, get live feedback, and basically really sort of hit the exam material in a very full-on, comprehensive way that covers pure and applied stats and mechanics. So it'd be lovely to see you guys there. That's great to hear. Thank you for the questions and answers as well. It was really helpful getting that feedback as we went along. So very well done to all of you. And yeah, have a good rest of your weekend. I'm going to just stop sharing that there. Thank you again. Hopefully see you at a session at some point soon. And maybe at the crash courses as well. If you're able to attend those, it'd be lovely to work with you guys through those crash course seminars coming up at Easter. So really well done. Have a good rest of your weekend. Keep well and hopefully see you at a session soon. Cool. Thanks, guys. Well done. Bye.